curse of using a tripod friggin' everywhere. All right, that's closer. It's not level. Okay. I think that should be close. All right, so I think that will get everything. All right, so we're gonna have a live stream solving things with Turing machines. And not necessarily Turing machines, but just a live stream to solve problems. And I need to make sure I can see all the messages. Live chat. All right, let's just make sure I'm going on the right channel. That might be good. Okay. Yep. All right. Let's just wait a bit for people to show up. I don't see anyone yet. Let's just make sure it actually is live. All right. So, what I would think would be good to for Turing machines to make a Turing machine for certain problems. So let's make a Turing machine for let's say A to the n, B to the n, C to the n, which is a nice language to have because one, it's not super trivial to implement a Turing machine for this, but also because it allows us to show that some Turing machines can do non-context free languages like this one. All right, so the way to kickstart this off is what would a Turing machine for, let's say, A to the n, B to the n look like? Well, the general way of approaching these, although there are many different approaches, but one way of doing it is if we have a bunch of A's followed by a bunch of B's, then what we can do is say, I'm going to mark one A off. So I'm going to put an X there. Then I'm going to mark the first B that I see with an X. And there are blanks after this, but and then once I mark an X over on this side, I come back, and then I will mark the X again. Every time I mark an A, I'm going to mark the B over here. And actually what I should do is use a different character here, because if I mark all of the A's with X's, and I happen to mark all the B's with X's too, then I would continue going left and I would hit the beginning of the tape, so which is not a good thing. So, let's figure out how to do the A to the N, B to the N, C to the N one. So typically what you do here is you treat the cases of where the string is empty, where the string is empty and when it's not empty. So if it's empty, then the first thing that we will see is the blank character. So the tape would just be blanks forever. So, and why would you want to do that? You don't have to do that, but it's nice because if it's not empty, then you know you're going to mark something along the way. So let's treat those. So I'm not going to name the states here. And actually, I should have given myself way more room because Turing machines are horribly large. Well, they're not awful, but they are pretty big. So I'm going to make a start state, and I'm going to handle the case of where we see a blank. So I'm just going to immediately skip right past that, and then I'm going to go to queue accept immediately. Okay. So if we're at queue accept, then we will obviously stop, but then otherwise we better see an A. So I'm only going to draw the transitions where we want to accept. So I'm not going to handle the failing transitions. I'm only going to handle the transitions where we have a possibility of accepting. We're doing the expected case. And then everything that's not expected, we can just send all those to queue reject and we'll be done. So here, our strategy, if we wanted to extend this idea over to for A to the N, B to the N, C to the N, is to say I'm going to have a bunch of A's, bunch of B's, bunch of C's. Then what I'm going to do is I'm going to mark one A, then mark one B, and then mark one C. And I'm going to have X replace the A, Y is just a character that replaces B, and Z is going to be a character that replaces C. So I'm going to have a bunch of Z's followed by some C's, and then, that was a horrible blank, so then blank after. So here, what I'm going to do is I'm going to do, actually, yeah, okay. So there's a lot of different design decisions we can make here. So what I'm going to do is I'm going to immediately mark one of the A's. So A is going to be changed to an X and move right. So what should we expect after seeing this A? Well, we should see some number of A's after the fact. So what I'm going to do is I'm just going to zoom past all of those. So this state you could probably call like skip A or something. Then at this point we need to see at least one B. But let's think about how this is going to go. So unfortunately with Turing machines we kind of have to plan what it looks like in advance, which is a little weird. But so at this point we have some number of X's at the beginning, and then we just converted an A into an X right here. So then we're going to have potentially some more A's. But we can also then have some Y's that are where the B's are. So I can have some number of Y's before the B that I need to change is over there somewhere. So I skipped over the A's, but I should also skip over the Y's, but I need to have the Y's after the A's. Although some of the logic that we're going to do is going to preclude that from happening, but I'm going to be safe and I'm going to have them be separate transitions. So I need to see at least one. Actually, no, I don't. Yeah. So the logic that's going to come later is going to preclude the Y's from occurring before the A's, which is something we don't want to do. So here I need to see at least one B and change that to a Y. So then there might be some more B's after the fact. And we might see some of the Z's corresponding to C. And then we're going to do something similar with the C's. change one of them, and then move right. Well, here, actually what we can do is be a little bit more efficient. So we have a bunch of B's here, and these were the converted B's to Y's. So I'm gonna have some number of C's that were converted to Z's. It sounds similar. And then I have a bunch of C's and then blanks. Well, if I convert this C into a Z, then there's no point in continuing right anymore because there's nothing else to check after there. Because we're only going to mark one of the things at a time, just going back and forth in between. So here, actually what I can do is move left. So in fact, I can move left. And then what I need to do is to zoom past all of this stuff, past all the Z's, all the B's, all the Y's, all the A's. And then when I hit an X, which must exist at this point, then I start over and do the same thing again. So here, so how are we going to design this? So this one is going to go left through everything else. So Z goes left. And all of these move right. That one moves right. Yeah, so this is the only one that moves left so far, and then this one. So then we need to go past all the B's, all the Y's, all the A's, and then at a certain point we need to see at least one X because we marked one in getting here in the first place. So I'm not going to change that X, so I'm going to move right past that. So at this point, if we're looking at a Y, then that means that we have no more A's left to mark. So let's figure out how that's going to work. So if I see a Y, then at this point we should see no more Y's or Z's. No more B's or C's. So here I'm just going to zoom past all of them. So just zoom past all of them. And then if I see a blank after the fact, then we're done. So we should accept at that point. And of course, these two states are exactly the same. Okay. Okay, so then now what about the other possibilities? So if we see an A, so then what can we do there? Well, effectively, we would just go back to this state. So I'm going to do that. So this transition comes back up here, and that gets converted into an X and moves right. And that's the expected case of what we want to see. And therefore, we can make a Turing machine for this, unless there's some weird case that I'm missing. Of course, we'll have all unwritten transitions go to key reject, and then we'll be done. Nice. So the Turing machines can get quite scary, but if you think about how you would approach what the tape would look like we kind of did here, then it's actually not that scary because all you need to do is just skip past certain sections and then handle, if you see one thing, then you can just skip past it. Actually, yeah. There was something I missed. Yeah. I shouldn't change the Z's along here. Yeah. I was looking at this and it seemed quite inharmonious with everything else, but yeah, so this should be good, unless there's some small thing that I'm missing. All right. If you have any Turing machine problems, just send them in. Oops. Nope, that's not what I want. There. Okay. So we can go over Turing machine problems. We can go over context-free things. We can do decidability. Talk about just general theory stuff. We can talk about the weather. whatever you wanna do. And I don't know where my phone is. Where'd my phone go? I'm using it. All right, so that's funny. All right, so that's a Turing machine for this particular language, which is not context-free, which is pretty cool. So thankfully, we don't typically write Turing machines to do certain things because it's just way too complicated for anything remotely complicated. And the Turing machines just get massively large. Yeah. So there actually has been some work in phrasing certain mathematical conjectures in the sense of having a Turing machine stop. So if a Turing machine with like 700 states that you make stops, then some mathematical conjecture is either true or false or something. So they are useful in some contexts, but not in like a truly practical sense. It's more just of an observation of like provable things that you can't do with computers. All right, let's see. If you have any questions, feel free to just put them into the chat. All right, so what would be a good other one? If you have any particular questions you want to go over, just feel free to send them in. But let's try to think of another interesting one. Yeah, what would be a good problem? So another one might be Turing machine variations. So like not like Elgar variations or something like that, but like a variation on the Turing machine model. So like if we allow, say like in this one, if we leave out some of the transitions that we did here other than this statement right here, then is that equivalent to the standard model? And of course it is, because that's what we prove in class. But typically, the ones that we focus on are multitape and not multi-track, non-deterministic. So multitape is where you have multiple tapes, and there's a independent tape head on all of the tapes. So we can be like looking at a different character on each potentially, and the tape heads move independently of each other. And then non-deterministic is where we have any number of transitions that we want on the same character read and state that we're in. So maybe we could have like A gets changed to a B and moves right on one transition, and another one that changes it to a C and moves left on another one. So it's not deterministic in that sense of what to do. And they're equivalent to the standard model. And the reasons are actually pretty interesting, not in any practical perspective, but rather the fact that it can be done at all, which is pretty astonishing. So for multitape, what you do essentially is you convert to single tape, or that's really what you want to do, but essentially what you do is you put delimiters between all of the tape contents. So you say tape 1 goes here, tape 2 goes there, etc. up to tape K for some number K, and then it just blanks after. And the devil in this is the details, because if we wanted to know, okay, what transition should I do over here in the single tape version, what you have to do over here is remember, in some sense, what the multiple heads over here were reading. So maybe this A was right here at that position, and then the B was maybe the first cell in that one, and then the C is somewhere in the middle in the other one, and that's not really super easy to figure out. So a way of getting around this is to use a different symbol for each one. So the A over there we can represent by like A with a little hat on it in here by saying this is a different character, but it corresponds to the A over there. And if we have a symbol with a hat on it, that means that in the original machine, that's what was being looked at. And then over here we would have a B hat, and then, but this may have a singular A. So we would have to maintain that we have exactly one hatted symbol in each of these tape sections. Another thing that's kind of annoying is if we're right at the very edge of the, let's say the second tape here, and we ask to move right on the second tape, then that means we have to shift all of this stuff over one position because we don't have the ability since we only have one tape here. So the way to figure out what the transition is to say, go start from the very beginning, and then look for the hatted symbols. So we would have let's say we're right here in this state, then what we would do is we would scan right, and then let's say that we could in principle see an A hat, but we can also see like a B hat and then a C hat on the first tape. And each one of those is going to lead to a potentially different transition. So then here we would have to scan right again, so scan right, until we can see an A hat, a B hat, a C hat again, and we'll have the same thing over here too, same thing here too. So we're going to have an explosion of states as we do this for all K tapes. In fact, we're going to have, if we continue doing this, we're going to have 3 to the K different states just at the output, which is insane. So we're going to have a whole lot of states over here of all the different possibilities that we can see. And so for each one of them, we're going to figure out what the transition is. So if we look through the different combinations that the multi-tape machine could see, we're just going to string all of those together in a bunch of different transitions that are just going to all come back down to a single state here. Actually, no, that's actually not enough yet. Because what we need to do is for each one of these outputs, because there's a whole massively large number of them, what we need to do is to scan left, and then when we find the appropriate symbol, we do the action that we need to do, which is absolutely monstrous. But the fact is that it can be done. I'm glossing over a lot of details because it's horrifically large. So no one actually does this, thankfully, but it can be done, which is pretty cool. And non-deterministic is a simulation approach that's not like this at all, but it's definitely a lot easier to get your mind around than the multi-tape one. All right. What questions do you have? Thank you for your work. Thanks, Oleg. Could you go over the doubly infinite tape? Sure. Absolutely. All right. So let's say that we have a doubly infinite tape. So here, there's no left-hand end. So effectively, we have an infinite tape all directions. Not all directions, left and right. And then there's an associated start cell. Okay, and it goes infinitely far in both directions. So what we can do is we can say, is this equivalent to the standard model? And of course, the Church-Turing thesis says yes, it is. But why is it here? So what we can do is to do some kind of cut and paste surgery here. So what we can do is to say, I'm going to make a little cut right here. Let's say right there. There's a reason I chose that cell, but it honestly doesn't really matter that much. And what I'm going to do is I'm going to take the left portion right here, and I'm going to swing it around 180 degrees. Okay, so yeah, so I'm going to swing this around and then paste it right here. So effectively what I'm going to have is a two-tape machine at this point. So then this part goes away. So I'm going to label the cell numbers. So let's say that was position 0, let's say. Well, it doesn't really matter what number it is as long as I give it a number. This is 1, 2, 3, 4, 5, 6, etc. And then the one down here would be, in principle, going the negative direction, but this would be -1, -2, -3, etc. So I'm going to have, I'll just put it below here. So -1, -2, -3, 4, 5, 6, and it just goes on. All right, so let's figure out what this. So let's say that we want to make a two-tape Turing machine out of this. There are other ways you can do it here, but so the original Doubly infinite tape thing only had one tape head. So it could, if we were stuck over here, let's say like in that position, and I like moved left to right in the Doubly infinite tape original thing, then that's just going to stay up here. It's not going to go down in here. The only point of contention is when I'm at the 0 point and I ask to move left, or I'm in the -1 position and I ask to move right in the original machine. And so therefore we would switch over here. So let's say that, well, here we, in the two-tape machine, so this is the two-tape standard Turing machine. That's what this is. So we would have to have a tape we need to have two tape heads for both of the tapes. So let's say it's in that position right now. So what we do is we try to maintain that only one of them is ever past this starting cell of both. Okay, so this one is past the starting cell of both of its area. So this one actually doesn't need to move at all. So what the transition would do, we would do exactly what the Doubly infinite tape thing says to do, except we would move this guy. Okay. And so if we move this guy, then we would just do what the Doubly infinite tape thing says to do. And let's suppose now that we're in a different situation. So like we were right there, and this guy was somewhere out here. Then effectively we would do the exact opposite of what the original machine would do, because if the Doubly infinite thing says move left, that means to go into a further negative cell. So therefore that means for us, that means to go right one position. So we would do the exact opposite direction of what the original Turing machine said to do. The Doubly infinite tape version would do. So then now let's think about the point of contention. So let's say that we were in cell -2 right here, and then this guy says to go left. Then what we would do is we would say, what do we do? Well, since we just moved left, we're in the blue tape right now. So therefore, if this guy says to move right, we just do the right thing. We would move to -2. Well, otherwise, if this guy moves left, then we transfer control over to this guy and then let it do its thing. If this guy says to move left, now we transfer control back to the blue guy. And then the transfer of control might go back and forth a few times. And then if this guy says to move right, then the black tape is going to take control here. So, and then we can continue from there. There are other ways you can do this. You can also treat these as two different stacks. So if you, it actually kind of looks like two stacks. Yeah. So so what you would do is you would represent this not by -1, -2, etc., but by 0, -1, -2, -3, -4, etc. And so these two cells would be identical. And then that would be a different way of approaching it by phrasing it as a two-stack problem. And so the only thing that you would touch are the things on the top of the stack. There are some details that are left out of this, but that's one way of approaching it. Yeah, that was a good question. Can you talk about building a Turing machine that recognizes U $V for strings U that are smaller than V? Yeah, okay, so I can do that. So let's say we have a language of U $V, such, and let's say that U and V are in 0, 1 star, like you said, such that the length of U is smaller than the length of V. Okay, so effectively we're just checking length. It doesn't matter what the strings themselves are, it matters what the lengths are. Okay, so what we want to do is, because this is a strict inequality, we need to see at least one thing on the right side, more than what the U part said. So, what's one way we can do this? Okay. Okay, yeah. So let's see. So let's make a start state. Then if we immediately see a pound sign right at the very start, then that means we need to see at least one character on the V side. So if we immediately see a pound sign, we need to see one character on the V side. So if I see a pound sign, I don't want to get rid of that, potentially. And so then I want to see one character. So what I'm going to do here is, the way I'm going to write this is that I'm going to have A goes right for all A that are not the blank symbol. Because if we see a blank symbol, then that means that it's empty on the right side, which is not something we want to do. And we would obviously go to Q except if that's the case. So then, actually, because we know the characters, we can, so this will take care of any other characters we want to write to the tape. And actually, we shouldn't see not a pound sign either, because the pound sign should only be in one place. We shouldn't be able to see two pound signs. All right, so here, what are we going to do? Well, we're going to do a marking strategy. So for each character on the left side, we're going to mark one character on the right side. So here, I'm going to mark one character. So I'm going to change zeros to, let's say, X's. And the characters themselves don't matter, so I'm just going to convert everything to X's. So here, I marked one character of the U side, so there might be some more characters of U that I haven't seen yet, so I'm going to just skip past all of those. So X, oh, I don't want to convert them yet. So 0 right, 1 right. And then change, skip past the pound sign, because we know there's exactly one of those, so we don't want to destroy it. And then what I need to do in the V part is mark one character too. But I need to skip past any other characters of V that I have marked so far, because I'm marking on the same side. You can mark them on the outer edge, and that would make it slightly smaller. It's just not a big deal here. Because we don't care about the strings being equal, we just care about the strings' lengths being equal. So here, I'm just going to skip past any X's that I have made, and then mark one character on this side. And then actually I'm going to move left and over here. So at this point right here, we're still on the right side, or maybe on the pound sign potentially, but we're still on the right side, not on the left side. So I need to skip past all of the x's, going left, and then skip past the pound sign. So pound sign left, and then skip past any zeros and ones that I have not marked yet. I want to go to the first one, which will make things a little easier. There are several other things you can do, but it doesn't have to be this specific approach. So then I want to skip past all of a bunch of zeros and ones that I have not marked yet, and then once I see an x, I must have seen one x so far, or changed an x so far. Then I'm going to go right past that, and that's it. So I didn't plan this in advance, but it happens to work here. So why does this work? So suppose that there is a 0 or 1 on the left side that I have not marked yet. So then here, in this state, I'm going to be marking 1 and skipping all the way to the other side where I mark 1 character. It doesn't matter. I haven't changed these. Yeah. So I'm going to mark 1 over here. Yeah, there's a slight error there. So I need to go all the way to the other side, mark 1 character on that side, go all the way back to the left side so that I maintain the counts correctly. So then here, I will, in principle, get to the first unmarked 0 or 1, as the case may be. So I'm going as far back as possible until I see an X, and then move right to the first character there. But now suppose that there are no zeros and ones on the left side to mark anymore. Then that means it's completely full of X's, which means that if we try to, when we move left here, there's no self loops that we're going to do here because there are no zeros and ones that are marked anymore on the left side. And so therefore, I will encounter the X immediately. And so then when I move right there, I'm going to land on the pound sign, which means that I'm going to try to go that route. And that's quick proof that this machine is correct. In fact, what we can do is to get u is equal to v in length. Actually, u less than or equal to v in length. We could make this state the accept state instead of that one. But this one right here is the thing that's helping us get the strict inequality here. So if we had less than or equal to, we would get rid of this last transition, but otherwise it would be exactly the same. There are many other approaches you could have done. It's not necessarily this one. All right. Okay. Yep, you are welcome, Michael. What other questions do you guys have? I can do this all night for 20 more minutes. Yeah, so I don't really like teaching Turing machines because for several reasons. One is that it kind of is too similar to PDAs. So the PDA versus Turing machine transitions are so similar that it's kind of hard to differentiate them. So in a PDA transition, it's going to be something like A goes to B, comma C, whereas in the Turing machine one, no, even that's wrong. So it's A, comma B goes to C, whereas in the Turing machine is A goes to B, comma the direction that you go. So the fact that this is so close yet different is what drives students insane from my experience. There are some things that we can talk about, and is a subject for talking about when I write the book that I'm eventually going to write is the diagram itself does not have to be formal at all. There's no point in having the diagram itself be formal. If you talk about the formal definition involving the set of states, the except states, and all that stuff, that has to be formal, obviously. But the diagram doesn't, because you don't feed the diagram into the computer. You feed the formal definition of the machine into the computer. So what we can do to make this better is to use English words. So what we can convert this guy to be instead is to say, well, here we're reading an A, popping a B, and push a C. But let's write that. So read A, pop B, push C. And then in the Turing machine version, we would say read A, write B, move D. And then that's a lot clearer to differentiate the two. And actually for DFAs and NFAs, we're going to have something similar. So if we have, like in a DFA, a singular character, now you have to identify which is which, although it's a little easier because there's fewer things on here. All that we need to do is to say, read A. The problem is now, this is kind of redundant in a DFA, but it's definitely not redundant in here. Unless you're just writing read, pop, push over and over and over. And you could just leave them out, but it's a lot easier to differentiate these two this way compared to a formal definition of the diagram, which is just absolutely not necessary. All right, enough ranting. Any other Turing machine type questions that you all have? I need some water. I already did that one, multitape standard. It's a horrifically large and complicated transformation. But I can talk about it. So the thing is that it involves a lot of details which are just absolutely not necessary in the sense of understanding the general idea of what it's going to do. If you want to implement it, you have to know all those details. But in terms of just understanding the general idea is just absolutely not necessary. So if we have a bunch of tapes here, so like here's tape 1, tape 2, up to tape K. So we have K tapes. Then potentially we could have a tape head in just any old position in any one of the K tapes. So then the transformation, glossing over so many details, is to say I'm going to make one big tape, and I'm going to put delimiters between all of these essentially. So essentially what we're doing is just copying and pasting all K tapes down here with delimiters in between. So tape 1's contents goes here, tape 2, up to tape K. Oh, and then blanks after the fact. And all that we're gonna do is try to, in this thing, since we only have one tape head, we need to be able to simulate a singular transition in the K tape thing, where these tape heads could do effectively anything, move left, move right, or even stay. They could change symbol independently of all the other ones potentially. So there's a lot of things that you can do. And the key is to how to actually maintain all of that information down here. The main takeaway is that we need to, or at least one way of doing it is to have an additional symbol for each one of the symbols in the original thing, where we say, if we had like say an A up here, then I'm going to have a different character here, maybe a dot or something. So it's a completely different character, but we're associating it with the A up here to say, this is where the tape head is if we were simulating the original thing. So then when we try to execute a transition in here based off of this, we would know, the tape head for the original thing was right here, where the dot is. And then when we say, maybe we move left, say, or in this thing, then what we do is we undot this one by changing the A dot to just a normal A into, and then the symbol over here would get changed to the dotted version of that. Sometimes you may, if we're right at the very edge right here of where the delimiter is and we say move right, we may have to shift all of this other stuff over one position and then come back and put a blank symbol in here. It's horrifically, and I haven't even gotten to doing the transition itself, because that's going to involve a large number of states, more than you can possibly ever imagine. It's so massive to make a singular, a single tape Turing machine for this, but it's possible. That's the point. If you want to actually implement this, please don't do that. But just that the fact that it's possible is what really matters. What is the best method to convert? Hold on. What is the best method to convert the language recognized by a Turing machine into a DFA? Well, note that it's just not possible in general, because we had the very first example we did today was A to the N, B to the N, C to the N, which you can't even make a context-free grammar for, much less a DFA. So generally, there isn't a method to convert a Turing machine into a DFA because, one, it's not possible in general at all to do, and two, if you have a Turing machine, well, you better be a fixed Turing machine, not one that you get as input, because otherwise you wouldn't know the behavior of the machine at all. So if you have a fixed machine sitting right in front of you, you might be able to reason about what it actually is doing. So one trick you can do is to note, if you have a Turing machine that only moves right, then it's effectively a DFA because you never inspect symbols that you've already saw. There is a more advanced thing that you can do. Is that it? Yeah, I think that's it. So this is a pretty advanced result. So if we have, if a Turing machine changes its tape movement, so this tape head movement, a constant number of times for all inputs, its language is regular. So that's one thing that you can do. The thing is that you can't actually, it's harder to actually make the DFA for that. Another thing you can do is if the input string is never modified, but you can go back and forth as many times as you want, versus here where you're limited, then a two-way, so it's effectively a two-way DFA that can move back and forth, and a pretty technical result that and you can actually make the DFA in this case, is equivalent to a DFA, a singular way DFA. And the proof of that I really wanted to do at some point, but I really want to understand the results so that I can explain it in a really easy way. But that would be one way you can go. So if you have if you never modify the input string, so Turing machines always write characters, but if you never write a different character than what was there, then it's effectively a two-way DFA, and you can then convert it into there's a conversion that you can do to make it a DFA. So there are some things you can do. There just isn't obviously a general purpose procedure. Here's another one. So another one is if the Turing machine runs in little o n log n time, then it's regular. Its language is regular. And that's actually a really tough proof. It's the hardest problem, I think, in the Sipser textbook. I did solve it when I was taking this class, and it is not at all easy. You have to talk about something called a crossing sequence, which is trying to analyze if you're going past a certain point, what are the possible things that you could have seen before and the things that you could have seen after. And if you run in strictly less than n log n time, then the number of configurations or something along those lines can't be super large. And so what you can do is make a DFA for all of those different combinations, it turns out. It is not at all easy to prove something like that. But if you wanted to use results like this, here are 3 great results. And I'm sure there are other sufficient results out there, like if the Turing machine has this property, then you can do that. So one is, I think, is that right? I think if a Turing machine never moves, it does not move left 3 times in a row ever, then it's regular or something like that. But these are definitely sufficient criteria. I don't know if there's a necessary one, but these are sufficient. Let's see. What other questions you guys have about Turing machines or things that you're studying, or just general shoot the breeze? Yep, sure, Michael. What kinds of questions do you have about Turing machines? Yeah, there isn't a whole lot you can really say about Turing machines by themselves, because anything that you want to prove about them is either super trivial or super undecidable to do. There's not really much in between that you can do, which is kind of interesting. But yeah, there just isn't a whole lot you can really say about them. And the fact that we don't even understand how 5-state Turing machines behave is really 6, but we don't know how 6-state Turing machines behave, as denoted by the busy beaver numbers. We don't know how long that the machines take. So if we can't even understand that behavior, then we're just screwed in terms of having any information about any larger Turing machines. And although there's a result that says if you can't prove things about sufficiently large Turing machines, it's just that even for really simple things, we can't prove anything really strong about them. With DFAs, we have vast amounts of literature about this. For context-free grammars, we have a pretty decent literature because there are some undecidable problems about them, but they're certainly way more studied than Turing machines. And it might be a good research project to look at some small state Turing machines, like try to determine the 5th busy beaver number or something. because those are actually quite complicated problems. That would give maybe some more insight into maybe slightly larger Turing machines, which would be really nice to have. All right, any other questions from you guys? How about a Turing machine that interprets a graph? Sure. So by that, I'm guessing you mean that a Turing machine that takes as input a graph and then does something with it. So that leads to something called an encoding. So an encoding is where you take the thing that you want to analyze and you convert it into a string, essentially. So there's three main representations of graphs, which are the edge list, the adjacency list, and adjacency matrix representations that you can write down as a string. So one thing that you can do, if we wanted to do like an edge list, let's say, and honestly, unless you're doing, you're looking at the actual runtime, the input format doesn't really matter. As long as you pick one of the three, it really does not matter. Because you typically just look at decidability of something. All right, so here, let's say we're given an edge list. So let's say that the edge list is, that's a set. So it's a list with like U1, V1, and let's say that these are unordered, but in order to write it as a string, you have to put 1 first. You could double it up by saying, if I write U1, V1, then I write V1, U1. But we can interpret this as an undirected graph just for now. So let's say that's U2, V2, up to UN, Vn. So then what would the Turing machine potentially receive? The thing is that as long as we agree on an encoding before we start, then we're good. And we can choose really any encoding that we want. There are lots of things we can do here. So one thing that we can do, although this really gets into something called a universal Turing machine, which I don't really want to get into. What we can do is just string them together. So U1, V1, pound sign, U2, V2, pound sign, up to UN, Vn. And then blanks after the fact. So then if I want to figure out what the neighbors of some vertex are, then what I can do is maybe in some workspace over here, what I do is I just scan left, maybe put some special symbol at the beginning to denote that we're at the front. And so I don't crash into the left-hand end. So maybe I want to know what V2 is next to. So then I just scan in here and I say, well, where's V2? Well, it's right here. So then if this is the second guy, then I look in the first one. If it's the first one, I look in the second one. And when I found one, I go all the way to the end and I put it down. Then I go back to where I was and then continue searching. So that actually gets into the idea of having the pairs in both directions, so that'd be easier logic-wise to find. So I wouldn't have to check whether this is the second one. I can just see whether it's the first. I just see when it's at the first one, and then I get the second one out of it. The problem is that we can get a very large number of vertices here, number of edges. And first off, we could get multiple edges in here. We can have an edge repeated in here, which is probably not a big deal, but we can certainly maintain that ourselves. But the one big problem here, what's the problem? The problem is that how do we represent these? Because we have to specify in the machine that's doing this what its tape alphabet is, or what its input alphabet is at least. So what we usually do is we consider a universal Turing machine, although this isn't working on Turing machines, it's working on graphs. But what we can do is we can encode the states here, the vertices as binary strings. So maybe we can say that U1 is corresponding to the string 0, and then V1 is 2 zeros, then maybe 3 zeros, and then 4 zeros. So if I see like a V1 over here, then the V1 is 2 zeros, so that'll be 2 zeros over there. And how do we separate these from each other so I know for a given run of zeros how many they are? I can put like a 1 in between, and then pound signs in between the pairs. So then I put a 1 in between. Actually, that should be 4 zeros, etc. Up to a lot of zeros with a 1, and then in this case there were 2 zeros, and then pound sign. So that'd be one way of encoding it. There are more efficient ways of doing it. Because the length of the string is going to be really long here. If I have n vertices, then on average these are going to be n over 2 in size. So therefore these are going to be about n in size. And so I'm going to have n times the number of edges. So the size of the representation is going to be much larger than what we would usually use for a real graph. So something you can do to fix this is to make these binary numbers instead of unary numbers, and then use a different character here instead of 1. That's one way you can go. But you can use an adjacency list representation. You can use an adjacency matrix. There are lots of different things to do, but you need separators in between to denote what vertex each one of them is. Kind of like how I did here. But effectively, you can do something similar. All right. Are there any other questions? Because if there are not, then I will end the live stream. Any other questions? One last question. One last question. One last question from Michael. What can it be? My horrible singing. If you're going to ask me to sing, then please don't. Just not even once. I'm not seeing a question. No questions anymore. No questions. So I'll erase this. How do you go from that binary representation back to graph and then run breadth first search through the Turing machine? Sure. So effectively it's just, how do you do breadth first search with the Turing machine? It's just helpful to not think about it. It's just, it'd be so nice not to think. Just say, Church and Turing they showed that computers today are equivalent to Turing machines, and we don't have to think. Don't think, just let it go. The live stream's over. Thank you for watching. No. All right, so let's talk about the breadth for search. So let's say that we were using edge list representation. So U1, V1, and let's assume that we encoded them correctly, but I'm just going to make this for simplicity. So what we can do is we would have to, for breadth for search, the usual approach is to say, what is the start vertex and what's the end vertex? So I need to, additionally to this, to provide the vertices, the starting vertex and the end vertex. So what I'm going to do is I'm going to have a special symbol to say the edges are over, so the edges are right here. And then I'm going to have the start vertex. So I'm going to call it S. So here's the start vertex. And it depends on what problem you want to solve. Typically, we want to do decision problems, which are yes or no answers. So breadth for search, in this sense, would ask, is there a path from S to T? And I hope you're doing well. Thank you very much. So start vertex, and we would need a separator here again. Let's do pound sign, although we could just use dollar sign because we want more money, right? So then T would be the end vertex. And then blanks after the fact. So this is typically what the format of a breadth for search problem would be. Not necessarily S and T after the edges, but along with the edges so that we can figure out where it is. Let's see. So how would we do breadth for search? Well, what we can do is, we always start over here. And what we do is we gotta maintain a queue of vertices to look at. So what I'm gonna do, oh God, this is gonna get horribly confusing. I'm just gonna do one take. So I'm gonna have a separator here to say all the work that's gonna happen is gonna be on the right side of that pound sign. Okay, so what I'm gonna do is remember the queue for, let's say breadth for search. Depth for search is gonna be similar because you just exchange a stack for a queue. It's the same algorithm otherwise. So what we're gonna do is the queue starts off with S in it. So what I'm going to do is skip past all the edges and say, get this starting vertex, put it right here. So I'm going to emulate the tape head with the marker. So we're right here. We're going to scan until we get past the dollar sign. Have this S right here, copy it over. So we're going to have a copy algorithm that will copy it over to here. And what we're going to do to maintain the list of, the queue of vertices that we need to explore is we're going to, we also need to maintain a set of vertices that we have visited so we don't revisit a vertex that we've already seen. So what I'm going to do is I'm going to have dollar sign be the delimiter between, so here's where the queue part is. And here's going to be the vertices that have been seen. And so we copy S over to there too. I know dollar sign kind of is an S basically, but I'm going to keep the queue right here and the vertices seen because we have, and so this is going to get horribly complicated because I'm going to have to shift things over quite a bit. So we go to the start vertex here, copy it here, copy it here. So then now what we do is we're going to take something off of the queue. So I'm just going to just wipe that clean. So it's going to be all blanks now, which is actually going to be okay. It's okay that we're going to have blanks there because if I want to add something to the vertices seen, I just keep zooming right until I hit the dollar sign, which I know exists out here. If we didn't know that exists, then we would have a problem, but we know it exists, so it's fine. So I take S off the queue, and what I'm going to do is go over, I'm going to scan left here, potentially to the beginning, although it doesn't really matter. then I'm gonna look for any time that S appears. So if I see, like, say V1 is S, just as an example, it matches. So then I'm gonna copy the other guy over into the queue and the vertices seen. So what we should do is to copy it to see if vertices seen contains this. So if this guy right here matches anything over here, just by scanning back and forth, then we're not going to add it to the queue. But if it's not over here, we're going to, let's say, write U1 down right there, and then it's right here. So I need a pound. I need some kind of delimiter in between all of the things in here, all of the vertices in here. So then I'm going to copy that into here. And then if we need to put something else in here, we're going to have this thing shift over, so that we would have we would make room for this, kind of like the multi-tape conversion. As I said, it's just nice. Don't think about it. Don't think. It would be actually better to have separate tapes for each one of these different things, so that we wouldn't have to like scan right way across back and forth. And it would actually make things significantly easier. But with a single tape, this is what you would have to do, or something similar to it. And then what you would do is, if you ever discover that T is the other vertex in here, in the pair that you look at when dequeuing, then you would immediately accept. So you would check if the thing that you're adding to the queue, or maybe the thing you take away from the queue, take off of the queue, is equal to the end vertex. So at the beginning, we should have done that. When we dequeued S, we should have immediately checked if S is equal to T. If it is, then we're done. Otherwise, we would add vertices to the queue and vertices seen. If we get to a point where the number of vertices represented here is the same as the number of vertices over here, then that means we have explored every vertex we possibly can, and so therefore we cannot possibly reach T. What you probably should do to make that a little faster is to maintain have a set of vertices of the whole graph listed way out here, so that you can just compare the two sets over here. Because in this format, it's kind of hard to determine the set of vertices, because you could have some vertices repeated many times. So if I just have like a set way out there, and it's pretty easy to implement a set with a Turing machine, just keep adding if it's not there. It's just so complicated to get all the details in. Just write it in Python or something. Python is nice. Turing machines are not for this. Turing machines are nice for a simple problem, like A to the N, B to the N, C to the N. Those are nice. This is not nice. Fair enough? All right. What other questions do you have? I definitely need some water. What other questions do you have? Good to hear, Michael. All right, so unless there's a very last minute question, I'm going to end the stream for today. So thanks for watching. I like the singing. Yeah, you're probably tone deaf. Well, thanks anyway. Thank you very much for watching Supam Deep. You're welcome. If you have any other questions, there's a Discord link in the description down below where you can ask any types of questions. Please don't ask homework questions, because then all I'll send you is the academic integrity video is not supported on the Easy Theory channel video, and you don't want to get that. So although there's some people I need to send that to right now, but Anyway, so thanks for watching. I'll see you all next time. Good luck on exams. So I'll see you next time.